638 shopping offers. So for this problem, we are giving a price array, and we are also giving a Spencer and the needs array. So for the price array is for the ith item. So for example, for the first item, the price is 2. The second item, the price is 5. And we are also giving this needs array. So the needs array means for the first price, we need the uh, quantities of 3, and for the second item, we need the quantities of 2. So in total, the total price is going to be 2 times 3 plus 5 times 2. It's going to be 16. But we are also giving the Spencer array. So the Spencer array's meaning is, so for each of the Spencer's I, the length is going to be n plus 1. So for example, the length of the price is n, and the length of the Spencer I going to be n plus 1 is going to be 3. So the first two items are going to be the quantities. So it means we have the first item, we have a quantity of 3. The second item, we have a quantity of 0. So this is a comparative to the needs. So the needs is 3 and 2. But if we are going to choose this Spencer offer, it means we're going to have a 3 and 0. Yeah. And we're going to have a price of 5. Yeah, so definitely maybe we want to choose a Spencer offer. Maybe it is the optimum. So for example, if we are going to, in Spencer offer 1, we can pay $5 for 3 and 0B. And in Spencer offer 2, we can pay $10 for 1A and 2B. So, because we need to buy 3A and 2B, so we're gonna pay $10 for 1A and 2B. So what left behind is 2A. So for 2A, the price is 2, so it's gonna plus 4. So finally, 10 plus 4 is gonna be 14. So 14 gonna be the best solution. It's gonna be the minimum price. Yeah. So currently, if you understand the problem, how are we gonna solve the problem easily? Maybe you're gonna think about maybe we're gonna try to use DFS, but is that possible? Because if we are going to use DFS, definitely we're gonna have 6 items, and for each of the items, so for example, we're gonna put them inside a tuple. So for each of them, it's gonna have a maximum value of 10. Let's just check that. Yeah. So for each of the needs I, it's gonna have a maximum value of 10. So if we are going to use the DFS directly, so inside it's gonna be the quantities. Maybe this is 4, or maybe this is 5, or maybe this is 9. But at most we're gonna have 6 items. Maybe this is 1, or maybe this is 7. Yeah. So this is the DFS. If we were to use memorization, so how many different cases? Yeah. So for each. Yeah. So this means there are gonna be too many different cases for the DFS. Definitely, we don't know if this is a tuple, and there's gonna be another tuple, and there's gonna be another tuple, and depending on the different numbers. So this is 4, 5, 9, 1, 7, or it may be others. Yeah. So if we are going to use this way, definitely it's gonna be time limit exceeded. Yeah, because for each of the time there are like 6 numbers, and for each number this maximum value gonna be 10. So this means 10 to the power, it's gonna become 10 to the power of 1, 2, 3, 4, 5, 6. Yeah. So instead of doing this, we're gonna use the bit manipulation, and we're gonna use a bit dp to zip the numbers. So for example, this is 4. We're gonna use 11100 to represent this 4, and for 5 we're gonna use 101, and for 9 we're gonna use 1001. So in this way, we're gonna connect all those boundary numbers. So for example, this is gonna become 100, 101, 1001. But as this number can be more than 8, so it's gonna be a 4-bit. So here we're gonna have a 0, here 0. Yeah. basically we're gonna turn this number into such binary numbers. So if we turn the numbers into binary numbers, so how many bits in total? So 6 times 4. So this means they're gonna be 24 bits. But those 24 bits are gonna become a number. So if it become a number, so definitely maybe this number is 10 to the power of 6. Definitely we're gonna use bit manipulation or bit DP to solve the problem. Otherwise, if we don't use that, basically here, this is the time complexity here. This is not 10 to the power of 6. It's gonna be much bigger. Yeah. Now we're gonna try to use a bit DP to solve the problem. So for bit DP, basically we're gonna need a state. So we need to get the initial state. So instead of setting the state to be 0, we're gonna set the state according to the needs. So first of all, we're gonna turn the needs array into a state, and and then we just need to find the minimum value for this state. Yeah. So first of all, for example, this is 2, 3, and 2. We're gonna turn 3 and 2 into a state. So for the first number 3, it is 1, 1, 0, 0, and for the second number it is 2. It's gonna become 0, 1, 0, 0, and this number gonna become 35. So this is gonna be the initial state. So finally, we want to turn this state into 0. If we can turn this state into 0, this means basically we've already met the condition. We finish all the quantities inside the needs, all the items inside the needs, and we just need to find the minimum value. But there are also two decisions we can try. So the first decision is that we can directly buy all the items. So for example, our needs is 3 and 2. We can use this 3 and 2 compare with the prices. It is 2, 5, and we have a number of 16. So this is the first decision. Another way is that maybe we're gonna use some offers inside the Spencer array. Yeah. So inside each of the offers, so for example, our first offer is 0, 3, 0, and 5. So we're gonna use this first offer, and we're gonna and then we're gonna compare all the items inside the offer. So if all the items like 3 inside the offer is less than and equal to the needs, so basically that means we can use it. Otherwise, so for example, if this pencil is 6, if this needs here is 3, it is more than the needs, definitely we will not use it. We will jump to the next one until we meet the condition. But for all the conditions, we're gonna choose the minimum value. Yeah. Maybe, so for the second example, maybe we can use once, and what left behind is that we're gonna use the needs array with the price. Yeah, because what left behind in the needs array times the price is what left behind for this one. Maybe we're gonna choose 2 items of this one, and what left behind maybe inside the needs array times the price. Yeah, so this is the DP solution for this problem. Now let's just define the problem, as the problem may be a little bit longer than other problems, because basically I need to explain why we're gonna solve it by using state DP. By using state DP, it means basically we can use a dynamic programming. The time complexity is going to be 2 to the power of 24 times 6 square. Yeah, basically it is 10 to the power of 7. If you don't use this method, basically it's going to be like a backtracking. Definitely you cannot solve the problem. Now let's just try to prepare the bit DP. So as the number is just from 1 to 10, this means for the bits we're gonna set a 4, and the state is gonna be start from 0. Yeah. Now we're gonna use the needs array to prepare the state. So for I enumerate the needs array, we're gonna update the state. So in bit manipulation, we're gonna use all, and for each of the number, it's gonna be this number n. Yeah. So n gonna be shift left, with how many bits? It's going to be I times the bits. Yeah. So finally we get this state. Now let me just print out the state to check what it's gonna return. Let me just return 0 at the moment. Yeah, because basically for the first example, if you remember right, it's going to be 35. We just want to check if this number is 35. As you can see, the result is 35. This means our state calculation is okay. Yeah. Now we're gonna return the DFS with the state inside of the DFS function. So here, as we are using the bit DP, definitely we're gonna use the bit manipulation. So we're gonna use our cas and DFS. So inside of the DFS, it's gonna be the current. Yeah. So this current is our initial state. So we put the state inside the current, and we're gonna directly use the DFS to solve the problem. DFS with memorization. So this is a bit DP. Yeah. First of all, we're gonna check the result. So this result is from the beginning. If we don't choose anything inside of the Spencer's array, if we don't choose any Spencer offers, we only choose the needs. So what's gonna happen? So for each of the state. Yeah. So this means we're gonna use a sum. So for the price times the number of items. So for IP enumerate the price. Yeah. But how can we calculate each of the item? So that is everything inside of the state. Yeah. So here we've already calculated the state, and now we just need to turn the state to each of the number. So for example, the state is like some binary numbers. Now we need to find this 3 and 2. Yeah, how can we find this 3 and 2 separately? We're going to use the bit manipulation to calculate, right? So here is our current. Now we need to shift to the right with I base. Yeah, we need to shift because here is shifted to left, make it bigger. Here we want to make it smaller, so it's going to be I times the base. Yeah, after shifting, because it can. Yeah, so for example, this is a binary number. We wanted to choose these numbers maybe. So after shifting, this number may be here, but there are going to be other numbers, so we're going to use a mask. Yeah, so after shifting, we're going to use a mask. So the mask is going to be, as this is a 4-bit number, so we're going to use a 0 x with f. Yeah, so this is for the bit manipulation, and this is for the mask, and we're going to use add with the mask. So here we calculate the result. So this is just one decision. We don't need to choose any offers. Yeah. So now what about we choose offers? So for offer inside the Spencer array, and we're gonna check each items inside the offer. So we're gonna use index j in range of length of the needs array. Yeah. So here we need to have a check if inside the offer, if this item, for example 3, is less than equal to the needs, this item 3, it is okay. But if it is more than that, definitely it didn't work. Yeah. Now we want to check the needs array. Yeah, for this item. So how can we check the needs array? It's gonna be the same. But before that, let's just prepare a next array. This gonna be the next number. Actually, this is a next state. So currently, we're gonna assign it to the current state, and next we're gonna update this next state because we are not sure when to update, but we need to have a check first. Yeah. So if yeah, so current we're gonna use this current to update the next. So if something with this current is less than the offer j. Yeah, this means for the offer, for the needs, for example, it is 3, but the offer is too big. For example, it is 5. If the offer is too big, definitely we want to break it. Yeah, otherwise we're gonna update the next state. Yeah, and else, this means yeah, we're gonna write this easily. We don't need to prepare a flag or something else. We can use a for else. So if there's no break, everything is okay. We're gonna update to the next, and we're gonna have the final result. So the final result is gonna be the minimum of the result with DFS with the next state plus the let me check the offer array. So it's going to be the last number inside the offer, which is going to be the price. So for example, it's going to be this price 5. Yeah. So now finally we can return the result. Yeah. Now the difficult part is how can we calculate this current less than the offer, or how can we update the next. So this is going to be the difficult part. Yeah. We have to do some more bit manipulations. Yeah, so how can we find this current number? So for example, this current number is going to be 3. How can we find this is 3? Yeah, we have to do the bit manipulation. Yeah. So the current we're gonna shift still. We're gonna shift right. Yeah, I, and inside is gonna be I times the base. Here gonna be j because our index is j times the base. So after shifting, we have to use a mask. So our mask is 0x x with f. Yeah. So for here, we just check this number 3. So for example, 3 inside the bit manipulation, it is at the right. Now we're gonna shift it to the left. So for the first number, yeah, we're gonna first shift it. After shifting, we're gonna use the mask. Yeah, so for this number 3, because inside the boundary representation, we put it at the left side, and this number 2, we put it at the right side. So for first of all, this is j equal to 0, and then this is for this 2, j equals to 1, because this 2 gonna become bigger, and we want to make it smaller. Yeah, so if this number, for example, this is 3, is less than the offer. Maybe this needs is 2. 2 is less than 3. It is less than the offer. We're gonna break, and we're gonna continue for the next offer. Yeah. Otherwise, if there's no break, we're gonna update the next state. Yeah. So what's gonna be the next state? So the next state gonna minus the number inside the offer. Yeah. So what's gonna be the number inside the offer? So it means it is this offer j. Yeah. But for the next, it is a state. It is a binary array. And for this offer j, it is just a number. So this means we want to turn this number into the binary number, and we need to shift it to the left to make it bigger. Otherwise, inside the offer it is smaller. How can we make it bigger? We're gonna shift it to the left. So how many bits? It's gonna be j times the base. Yeah, there's a lot of bit manipulation, and we have to be careful. Otherwise, we're gonna make mistakes. Yeah. So currently, this is my basic pattern for this problem. If you understand right, from the beginning, we're gonna prepare the state, and then we're gonna use call the DFS for this state. Yeah. So the time complexity here are 2 for loops. This is like 6 square for the 2 for loops, and for the state it is 2 to the power of 24. Yeah, so the final result is gonna be 10 to the power of 7. So this is why it's small. But I'm not sure if I can pass. I have to test. Yeah, let me just run it. As you can see, it works. Yeah. Now let me just submit it to check if it can pass. Yeah, as you can see, it passed for all testing cases, and it's pretty fast. Yeah. So the idea is that how we gonna use bit manipulation and with bit mask and with bit DP to solve the problem. If you are not going to use bit DP, so here inside the current, it will not be a number. It will be some tuples, and it will be different numbers. Yeah. And how you gonna update each of the number is gonna be a difficult part. But here, while we are using the bit DP, we're gonna update them together. Yeah, but even if you can update it by using the you can update by using the tuple, it's gonna still be time limit exceeded. Yeah, but here I don't want to explain if it didn't work if we are not using bitDP, but bitDP is a good solution for this problem. Thank you for watching. See you next time.